disappeared. It's okay.
Improvise, Sheila.
Yeah, I don't need a laser. I really don't. I'm not going to go through regression results or anything, so it's fine. It's totally fine.
Start in about a minute.
Sounds good. Thank you. No problem.
Good afternoon. Let's get started. Let me begin first by announcing our speaker next week. And there is a change in the sense it's not going to happen obviously next week. It's Thanksgiving's holiday. But 2 weeks from now, the talk is also not on Thursday. That's the only change we have had so far this semester. So the next symposium talk is actually on Tuesday, December 3rd. And it's 3:30 p.m. in chemical engineering, and you will all, most of you are on our listserv, so you will receive more information about that talk. Our speaker is going to be Tariq Samad, who is a corporate fellow at Honeywell Automation and Control Systems, and he'll talk to us about control for smart grids, applications, and opportunities. And you'll receive more information via email about the location and timing as well. It's a tremendous pleasure, and really I mean it, to introduce to you Dr. Sheila Olmstead, who is a colleague of mine at the LBJ School of Public Affairs. This is her first semester here. We are absolutely delighted at the school and also broadly at the university that she's here with us. She brings really much needed expertise in environmental economics at the school and the university. She is an environmental economist herself. She has really done a lot of work in a variety of areas. And just to give you a sampler of some of the important issues that she's tackling right now, externalities associated with shale gas development in the United States, impact of federal fire suppression policy on land development in American West, free riding in dam placement and water withdrawals in transboundary problems, and also regulatory avoidance under the U.S. Safe Water Drinking Act. So this is just to give you an example. Over the last decade or so, much of her work has focused on water management issues, water conservation policy, water demand. So that's really been a core focus. But she has also been very, very active and engaged in research more recently, also in broader issues of climate policy and energy policy. She is really an accomplished researcher and has published in all the top journals, including the paper that she's going to present today that was published in the Proceedings of the National Academy of Sciences, which really is one of the top journals, period, in any field for that matter. Her work has been funded broadly by NSF, by DOE, and all sorts of other agencies. She wrote a book in 2000, co-wrote a book in 2007 on markets and the environment. She sits on the board of directors of the Association of Environmental and Resource Economists, also on the advisory board of the International Water Resource Economics Consortium. She holds a PhD degree from the Harvard Kennedy School of Government, a master's degree from the LBJ School of Public Affairs, so she actually went to school here, and a bachelor's degree from University of Virginia. Those are all the things that's on the paper, but I'll tell you that personally, I am very, very delighted to have her in the school. She's actually my faculty mentor. I interact with her to learn about things, and one of the things which I think at the end of this talk you will hopefully share with me, what has struck me tremendously is her immense grasp of where her work fits into the broader area, what has been done, what are the most important questions to ask, and absolutely perfect approach towards the methodology and the data and what can you really tease out. So that has struck me as being really, really important, especially if the types and the nature of questions that she's dealing with. So such a delight and pleasure to have you, Sheila, here.
Thank you so much. I I think that goes on record as the nicest introduction anyone has ever given me, so thank you so much for that, Varun. I, too, am really pleased to be here. As Varun said, I'm an alum of UT, so it's just like coming home to be back here. It's very exciting for me. And the paper that I'm going to talk about today, I feel a little bit like an interloper at the Energy Symposium because this is, I've worked on climate change a little bit, on climate change policy, but I really kind of got into my interest in the work that I'm going to talk about today on shale gas development because of my kind of correlated interest in water resources. Okay, so as Varun mentioned, most of my past papers, most of my current papers are on water resource management, and so that's really the kind of angle from which I'm coming at this material. And so thankfully I have lots of colleagues and many of my collaborators on this work actually who have much greater expertise in energy economics than I do, and they have helped and sort of corrected me along the way as I thought about research design. But as he mentioned, what I'm going to talk about today is a paper, mostly about a paper that was published in the Proceedings of the National Academy of Sciences earlier this year, where my colleagues and I looked for impacts on rivers and streams in Pennsylvania from shale gas development, various aspects of shale gas development in Pennsylvania. And the way this fits into the broader picture is to sort of think about, as I'm talking about the impacts that we'll discuss for Pennsylvania, I want you to kind of be thinking in the back of your mind, well, how are these relevant, or are all of these effects relevant to other shale plays where we might be concerned about similar issues or not? And we can discuss that hopefully in the Q&A. So I don't need to do too much of an introduction to shale gas here in this audience. I'm sure many of you are aware, particularly being here in Texas, that this is a major, and I put in quotation marks, new domestic energy resource, because it's not new in the sense of being sort of newly discovered. It's something we've always known has been there, but it's newly exploitable in an economic sense, right? So it's really what we're talking about is a source rock for conventional oil and gas reservoirs, which can now be exploited directly as a result of the combination of technological advances that have occurred mostly in two areas with respect to hydraulic fracturing and horizontal drilling. Okay, so we're grateful from that. From an economic perspective, right, U.S. production alone is underway and is increasing rapidly, maybe a little bit less rapidly in gas than in oil right now because of the differential in prices for those two resources, or differential in increases in prices for those two resources. But what you can see here is that if you kind of look at the current day, shale gas, it represents, somewhere, maybe just less than a third of current production, or between a fifth and a third of current production in the United States, but is expected to comprise 50% or more going out to 2040 and beyond. So in terms of economic benefits, and again, as Varun said, I'm an economist, so we have to sort of talk about this stuff first and think, well, what are some of the benefits of these recently exploitable discoveries or economically exploitable discoveries? Well, the benefits for consumers and producers from low gas prices and from new regional economic activity associated with the extraction techniques that are being used in many parts of the country are just huge. Okay, so this is just a graph of natural gas prices, spot prices between January 1992 and January 2012. And prices have come up somewhat since then, but the main kind of trend, I'm pointerless here today, so I'll just kind of move over here. The main trend I want you to sort of draw your eye to is the fact that we had basically an upward trend. There's a lot of volatility. There's always a lot of volatility in most commodities prices, and natural gas is no exception. So the lines are sort of moving around a lot. But in general, you can see that, as of, say, the mid-2000s, there was a sort of upward trend in prices, including some pretty high spikes. And the expectation in the early part of the last decade was that upward trend would in fact continue, and that the United States would become a significant importer of natural gas from countries like Russia, possibly Venezuela, and some others. And what we see is, as around sort of 2007, 2008, we see the price really begin to come down very significantly, and that really is in large part due to the sort of coming online of shale gas resources and the sort of shale revolution. And that downward trend, again, well, we're going to expect some volatility around that trend. In general, we'd expect prices to be much lower as a result of these discoveries and this sort of new technical capacity that we have than we would otherwise have expected them to be. Okay, so the counterfactual was the U.S. was going to be a major gas importer. Now, right, we have firms that are lobbying for export permits. We have, right, trying to convert what had been new, basically, import terminals into export terminals, and so on. So it really has completely changed the landscape of natural gas markets, including that in the United States. And in addition, we have some potential co-benefits for the environment that I think have sort of yet to be sufficiently quantified. One, and perhaps most importantly from an economic perspective, just a domestic economic perspective, is that as gas displaces coal in things like electricity production, in the United States, we would expect to have much lower levels of local air pollutants emitted, and that has major implications for human morbidity, mortality. Economists can and do monetize those things. I know that sounds a little bit morbid, but in fact that does happen in sort of regulatory standard setting and so on. And so we could actually think about what the benefits of those reductions in local air pollution mean for local and national economies. And climate change as well. So certainly when you burn natural gas, you produce less carbon than you do when you burn coal. So that is sort of without question. But there are still some remaining questions about methane and whether methane, which itself is a potent greenhouse gas, is emitted in what quantities throughout the shale gas production process. And many of those questions are being addressed right here at the University of Texas by folks in engineering and elsewhere. So that's an important kind of remaining open question which is beginning to be resolved just by good research. But what I'm here to talk about is the fact that the public seems to be really, really worried, more worried in some parts of the country than others. And the focus of their worry has been mostly on impacts, potential impacts to water resources, and several different potential impacts. But you don't have to look far on the web, or even if you go to urban settings in the Northeast, the Mid-Atlantic, you see lots of signs of this kind of opposition. You see sort of placards on bus stations in cities like New York and Philadelphia that talk about the potential risks of shale gas to water resources. You see political cartoons in the national press. Some of these are not sort of very accurate relative to what's known in the sort of science literature or the empirical literature on what the potential impacts might be. But yet there's a lot of concern. I think that top picture in the middle is sort of a still from the now famous movie Gasland. And so one approach to this is to say, well, you know, how significant are these concerns really, right? What would the experts say about the potential risks to water resources from shale gas development, okay? And so, as Varun mentioned, I'm a newcomer to UT, and the past 4 years I spent at a think tank in Washington called Resources for the Future. And at Resources for the Future, we got a big grant from the Alfred P. Sloan Foundation to do some work where we sort of looked at what some of these potential risks might be. And the first thing that we had to do, because the literature was so thin on such a sort of new process and trying to understand what the risks might be in an academic sense, we had to kind of go out to experts and do a sort of expert elicitation process, a survey, where we asked people, 215 different respondents in industry, I think 75 respondents were in industry, 63 were in academics, and then the remainder were in either NGOs or government positions. Okay? And we asked them to basically rank. We sort of created a big matrix of about 264 different risk pathways that went from some shale gas activity, like the clearing of land for infrastructure development, or the use of trucks for bringing water to well sites and so on, all the way to potential impacts on things like human health or water quality. And we asked them to rank those and sort of think about which ones were the potentially highest priority risks, those that were deserving of future attention either from government regulatory agencies or from industry changes, sort of voluntary changes in industry behavior. And what we found when we did that was a remarkable, at least to us, we thought, given the contention surrounding the issue that we, especially sitting in Washington, D.C., a remarkable degree of consensus. So if we took each of these 4 groups and we ranked their sort of top 20, or stacked against each other their top 20 high priority risks, 12 of those, the little sweet spot in the middle of this Venn diagram here, were held in common across all 4 of those groups. Okay, that's kind of amazing considering that includes industry and NGOs, which we would think were relatively far apart on what some of the high priority risks would be. And that doesn't mean there was agreement on everything else or anything like that. Okay? But in general, there was somewhat of a significant agreement on what the high priority risks were. And when we looked at those, I don't expect you to be able to read each of these sort of line items, but basically each of these endpoints or each of these pathways represents one of those 12 risks that was sort of in that sweet spot, identified by all the groups as being relatively high priority. And of those 12, 7 of them had to do with surface water resources. Okay, and then there were a couple of potential groundwater impacts as well. And when you add up all the kind of surface water and groundwater, right, we get to about 9 out of the 12, right? So a very significant fraction of those sort of consensus risks seem to have to do with water resources. Okay, so on the one hand, you could say, well, there's all this public concern, right? Maybe that is an indicator, right? And we sort of combine that with the expert elicitation. Maybe it's an indicator that this is something that we should be looking at. But I'm going to offer you one way to think about this issue that's going to sort of take a change in tone from what we hear in the public debate over this issue. And that is that certainly it might be true that some of the risks to water resources that are posed by different aspects of shale gas development might be new, might be poorly understood. But I think that what we're finding in our research, and I'll show that to you in some detail in just a minute, and I think you sort of add that together with what else, what other groups that are doing research on this issue are finding out there in the literature. And I think I could summarize that by saying that a lot of these are sort of what I would call run-of-the-mill externalities, right? These sort of costs that are imposed by the operations of private firms that aren't necessarily going to be taken into account in their own decisions about what and how much to produce and where. From industrial activity, right, that they don't really have to do specifically necessarily with any piece of sort of the shale gas development process, and that doesn't mean that they're not important, but they're sort of run-of-the-mill, kind of familiar pollution problems, if you will, that are simply likely to occur on a really, really large scale as a result of very, very fast and sort of rapid, large geographic scale development of these resources, and in some new places. Okay, so there's, as I said, a lot of the opposition that we were hearing and looking at was happening in the Mid-Atlantic and the northeastern states, which haven't been for a long time kind of major oil and gas producers. Okay, so what kinds of externalities or kind of pollution impacts am I talking about? I'm talking about things like, wastewater treatment and disposal. Okay, you'll see that that'll become a sort of important player in the analysis that we look at. Large-scale water withdrawals is something other folks have worried about, including folks here at UT. Stormwater runoff. Okay, I'll tell a sort of story about that in our research as well. Again, sort of conventional things that happen with any kind of industrial activity, any kind of land clearing activity and waste producing activity, but things that we sort of have a pretty good handle on how to deal with them. Okay, so my sense, given our research thus far, and that's not to say that this wouldn't change over the next 5, 10, 20 years, right, as everything plays out, is that when I talk about the kind of big impacts to water resources, meaning those that we could monetize and that would turn out to be pretty large, are probably going to be in this latter category, right, that reasonably familiar problems just happening on a really big scale in places that, right, we may not have seen a lot of this in a long time. Okay. So as I said, the sort of one of the driving forces behind that sort of preliminary conclusion is an analysis that I've done with several of my colleagues at RFF, so Lucia Muhlenbachs, Jishang Shi, Jessica Chu, and Alan Krupnick, that appeared earlier this year in the Proceedings of the National Academy of Sciences. And what we do in that paper is we use regression analysis, a very simple framework. Okay? We exploit spatial and temporal variation between 2000 and 2011, so over an 11-year period, in the proximity of both shale gas wells and shale gas waste treatment facilities, or just industrial waste treatment facilities that are treating shale gas waste along with other parts of the waste stream. And the sort of differences in proximity between those and surface water quality monitors to estimate the impact of shale gas development on concentrations of two contaminants. And what I mean by that is this is just two pieces of a map that I'm going to show you that's much bigger in a few minutes. But it gives you some sense for what the variation looks like just within the state of Pennsylvania, the sort of portion of the state of Pennsylvania where these resources are being exploited. So this is an area right around Pittsburgh, as you can see in the sort of far southwest corner of the state. And the red X's are wells, the green dots are surface water quality monitors, and then the triangles are waste treatment facilities of one type or another that are permitted under the Clean Water Act to receive, treat waste, and release treated waste to rivers and streams. And the ones that are filled in red are those that at some point between 2000 and 2011 accepted at least one shipment of waste from shale gas wells. Okay, so that's basically the kind of lay of the land. And what we're doing is we're saying, okay, well, some of these green water quality monitor dots, some of those are close to wells, some of them are close to waste treatment facilities that have been receiving and treating waste and releasing to rivers and streams, and some of them are far from those types of facilities. Okay, and we're going to exploit that sort of difference, and that difference changes not just over space, right? You can see this is down in the corner by Philadelphia, so down in southeastern Pennsylvania, where there's essentially no wells, okay, but still we see some waste treatment plants that are receiving shipments from wells, mostly in the north central part of the state. Right, and so these green water quality monitors here are going to be relatively less affected by that kind of development activity than the ones on the left-hand side. Okay, and it's that kind of difference over space that we'll exploit. And then, of course, this sort of layout of the wells here on the left-hand side comes in over time, right? They don't all just appear. These were the wells that were there around Pittsburgh in December of 2011, but they sort of folded in over time, right? Beginning, essentially in 2004, but really we see the drilling pick up in 2007, 2008. So a pretty short period of time. We start seeing more and more of these red X's on the map, okay? And same with the waste treatment facilities, right? Some are accepting waste at some points and not at others. And so we're going to exploit all of that variation in the regression framework. Why do we look at these two contaminants? The two contaminants that we looked at were chloride and TSS, or total suspended solids. And here you kind of have to look at, first what's feasible. Okay, we're looking at water quality monitors on a map. I'm going to come back to the map in just a minute. Oops. Okay, here it is. We're looking at water quality monitors across the whole state of Pennsylvania. Those are, again, those green dots. And so you need, sort of monitors that are picking up the contaminants that you're interested in over enough time, right? You've got to have monitors that are monitoring for something right before and after shale gas comes. And right in places in the state where we have shale gas and where we don't have shale gas. So you kind of sort of looking for contaminants that fit that bill just in terms of what we're looking for. Okay, we have to look under the light post to some extent. Two, you want to pick some contaminants that are potentially correlated with shale gas development. Okay, and these two are strongly correlated or potentially strongly correlated with shale gas development for reasons I'll talk about in a minute. And then three, you want to pick something that is potentially important, that could potentially either in and of itself have an important economic impact downstream, right, by increasing treatment costs for something else, like a drinking water treatment plant that might be withdrawing water downstream, right, or it might have impacts on ecosystems or human health. And for both of these, they themselves have their own impacts, okay, so chloride and TSS, you sort of don't want too much of those in any river or stream in and of themselves, but also both of them are sort of indicators of other stuff that might also be in the water, and I'll give that sort of greater treatment as we talk about the study. Okay, so first let me talk about chloride and tell you why it is, sort of the different pathways that we thought through which chloride might actually end up in rivers and streams from shale gas development. So basically the process here, right, is that a shale gas operator, right, wants to drill a well. It's going to have to locate someplace near available stream water. Okay, it's going to take a lot of raw water resources to hydraulically fracture that well. On average in the Marcellus, it's sort of 3 to 6 or 3 to 7 million gallons per well. And then they have about 6 wells on a pad, usually. Again, that's an average. And so you're going to be making lots and lots of tanker trucks, right, for every well pad. So you've got to be reasonably close to a water resource. And then you're going to truck that water. Sometimes they're using pipelines to move fresh water, but often it's trucked. And you're going to store it at your gas well site. Okay? And then that's where you're going to add your fracturing chemicals and your sand, in reasonably small proportions in comparison to the water content. But you're going to be adding some stuff to that. You're going to fracture your well. And once you sort of pull the plug and not all, but some fraction of that water flows back to the top of the well, in large part in Pennsylvania what's happening now is a lot of recycling, right? And that was happening to a much smaller extent during our study, but it was still happening. So there's two things that could happen to that water as it comes back out. One, it could be recycled and trucked to the next well pad, usually partially treated in some way, okay? Or two, it's going to be going for treatment and disposal, okay? There are several different ways in which that could happen, but in Pennsylvania the main pathways are either to deep injection wells, okay, where we basically, most of this is in the southwestern part of the state, shipments by truck to deep injection wells in Ohio, because most of Pennsylvania is not geologically suitable for those kinds of wells, which are very effective disposal mechanisms in most parts of the western United States. Or going through wastewater treatment plants and then back, right, partially treated into rivers and streams. And so in our view, there are sort of two ways in which we could imagine that this briny waste, okay, this is why we're looking for chloride, okay, it's a major sort of component of total dissolved solids in the flow back and produced water that comes out of these wells. There are two ways you could imagine that could end up in rivers and streams, okay. One is through this process, right, we're moving millions of gallons of, water, and then, eventually it's containing very high levels of total dissolved solids, chloride in particular. We're moving it around in very large quantities. We're sometimes storing it. We're moving it by truck. So and all of that's sort of happening around a well site, right, or a series of well sites if you're recycling. So one thing that you could imagine, and this is something that I think is very much in the public imagination, is that you would have a reasonable chance for accidental releases in that process. Okay, and so there we would be looking for impacts of increased chloride downstream of well sites, if that's what you think is happening, right? That's what you would be looking to detect. And then another pathway would be that when these shipments go to wastewater treatment plants, the wastewater treatment plants are not desalination facilities, right? That's a very expensive thing to do. And so they can remove a lot of the contaminants that are in that waste stream, but certainly not all of the chloride. And so one thing, what they're doing, right, is they're doing some treatment. They're doing a lot of dilution, right? There's sort of a flow coming through the plant, and there's a bigger flow, hopefully, in the river, right? And they're releasing, in a timed sense, so that they can dilute some of that flow. But we might still be able to detect, right, if there's partially treated waste in large volumes entering rivers and streams from shale gas waste treatment, we might still be able to detect that chloride downstream of waste treatment facilities. Okay, so two paths for chloride potentially: from wells, from moving all this sort of briny fluid around, or through waste treatment facilities, right, from the sort of partial treatment process. And then for total suspended solids, the story is very different. Okay, here what we're looking for is more a story about, each shale gas well site or well pad is a construction project at some point. Okay, and construction projects are usually required to have stormwater control infrastructure in place so that when it rains, right, and stuff starts running off this newly impervious surface, right, that used to be forest or agricultural land, that's in Pennsylvania generally the two types of land use that are getting replaced by shale gas development. As the sort of rains and the runoff, right, starts to happen, you're trying to prevent some of that, the sort of soil erosion and the sedimentation that would happen downstream of those things by installing infrastructure like what you see here on the right, just retention ponds and other kinds of things like that. And under the National Energy Policy Act of 2005, federal law basically exempts oil and gas construction sites from the basic kind of construction site stormwater requirements under the Clean Water Act. And so in Pennsylvania, we certainly have some state-level standards in place. There are many operators that use effective stormwater control practices, even though it may not be required given the size of their well pad or the sort of well site. But land clearing and construction can still increase runoff if we have some sort of inadequate control infrastructure, or even if we have the control infrastructure in place, right, it could still be increasing erosion. You can't eliminate it, right? It's only going to control it. So for the total suspended solid story, there really mostly what we're looking for is an impact just from well sites, right? If we think that there's erosion and sedimentation happening as a result of all this construction of wells and pipelines and so on, then that's what we'll look for from well sites. Okay. So what do? First, we go out and we get a whole bunch of data. Okay, we get data from lots of different sources. The water quality monitors, those green dots on the map, those come from EPA's storage and retrieval database. So that pools together water quality observations that are sort of from monitors maintained by USGS, EPA, other agencies. Okay, and so we're picking here just the monitors that pick up at least one of the two contaminants we're interested at least once over the time period. Okay, so all these green dots tested for either chloride or TSS or both at least once between 2000 and 2011. We know when each well was drilled. Okay, this is from the Pennsylvania Department of Environmental Protection and also a supplementary data set from the Department of Natural Resources, which is more the kind of oil and gas permitting institution in Pennsylvania. And through sort of combining those two sources, we get to about 5,000 wells by the end of 2011. And lots of other data sources, as you can see, for some of the other things that we're looking at. The waste treatment plants, sort of, again, a key variable that also comes from Pennsylvania Department of Environmental Protection, which tracks the shipment of waste from wells to facilities and so on. And then this is what the map looks like. Okay, so again, the green dots are the water quality monitors. The red X's are the wells. Okay, the open triangles are waste treatment facilities that haven't accepted any shale gas waste. And then the red filled-in triangles are those that have. All right, so what do? Here we run lots of different regressions. Some of the regression equations have up to 2,000 different controls in them. Mostly what we're trying to do is sort of sweep out any variation that would sort of screw up our ability, right, to estimate that potential causal relationship between shale gas wells or shale gas waste treatment facilities and the downstream pollutant concentrations. And what we find is very much consistent with the sort of prior that I set up for you earlier. Okay, we find that we don't see any statistically significant impact of shale gas wells on downstream chloride concentrations. This would suggest, right, that there's sort of no systematic way with which brines, right, from flowback, from produced water, are making their way into rivers and streams at well sites. Okay, right, so it's not consistent. This result is not consistent with systematic contamination of rivers and streams from accidental releases or spills or that kind of activity. Okay, that is, again, right, in the multiple sort of regression framework, we can't rule out individual instances of things like that, but we can say systematically, right, we're not finding evidence of that. But we do find that the release of treated waste, or I should say partially treated waste, to surface water from these permitted, the sort of red triangle waste treatment facilities does increase downstream chloride concentrations. And interestingly, right, there's a lot of discussion happening at the state level and at the EPA during the period of our analysis about whether these facilities should be accepting waste. There are facilities that are able to accept waste at the beginning of our time series, but then become restricted in their capacity to do that toward the end. And what we look at, and again, we were sort of early to really understand what the impacts of these regulatory changes would be, but we do see some indication that the regulatory changes were sort of working in the right direction. Okay, the effect of this waste treatment on downstream chloride concentrations is definitely more strongly associated with the facilities that were targeted by these changes or these sort of restrictions on the ability to accept waste than the ones that were not. So that's an important result as well. And then for suspended solids, right, we don't see an impact of shale gas waste treatment on downstream total suspended solids concentrations. And that's not terribly surprising. So I said these facilities aren't desalination facilities, but they are very well equipped to remove suspended solids. And it turns out it looks like they do that, at least whatever's coming through the shale gas waste. But on the flip side, right, the wells themselves do seem to be associated with this increase in downstream suspended solids concentrations, right? So again, suggesting that the process of clearing land, putting in impervious surface, and so on, is increasing erosion and sedimentation from well sites. It's harder for us to say in our results what exact activities are causing those impacts, and I'm happy to address that in the Q&A as we talk about that. And in part, I think that's because we lack data on the physical location of things like pipelines and roads. And the estimates are, in terms of the sort of footprint taken up by infrastructure, that there's a much bigger footprint for pipelines than there are for well pads. Okay, so we think what we're seeing is a sort of infrastructure impact, but we'd like to have more and better data on the location of some of those big infrastructure projects as well. So kind of coming back to where we started, right, we do find that shale gas development causes this sort of increased contamination in Pennsylvania rivers and streams. We find that almost right from the beginning, because in 2011, right, end of 2011, where our study stops, we're really only about 4 years right into the sort of intensive development, and now we've got an additional 2 years that we could potentially look at. But the problems that we identify are not really the problems consistent with those pictures, right, that I sort of showed you earlier in terms of public concern, right? They are more conventional pollution problems, right? Wastewater treatment and disposal. This is something, right, we do for lots and lots of industries. We do it in municipal settings, right, lots of different settings, and erosion and sedimentation. Again, a pretty kind of classic pollution problem. And notably, we don't find systematic statistical evidence of accidental releases, right, which is, I think, what the public has more in mind when they're thinking about the potential for pollution from shale gas development. And so given these impacts, the scale of current and potential future development is worthy of concern. Okay, so when I talk about scale, if you think about Pennsylvania in 2013, so now, as I said, in 2011, we were at about 5,000 wells by the end of the year. Now here in 2013, we're about 7,000 unconventional gas wells. How many would you guess are expected by 2030 in the Marcellus Shale? Anybody have any ideas? 30,000. So there are a lot of different estimates out there, and of course that's going to be driven by prices and lots of other things. The Nature Conservancy has done a really interesting study, and their medium development scenario suggests 60,000 wells, okay, by 2030, which is a pretty fast rate of increase. Okay, it's about 12 times what we saw in the end of 2011. So, right, if you're worried about these pollution problems, it's not to say, right, they're conventional problems, we don't need to worry about them. They are interesting, important problems with the scale of development. We have to think about how we're going to manage that, but they're sort of not necessarily the type of concern that sort of most people in the public, I think, would have first on their lists about water quality impacts. Okay. Another important question comes up, right, so when I talk about this work, a lot of people, the first thing you think is, well, actually there's a lot of recycling going on, right? So you talked about, Sheila, the big problem is disposal of all this waste, but can't they just, you said that they can recycle it, can't they just kind of keep doing that? And in fact, yes. Okay, so as I mentioned, that sort of loop of taking the flowback out, right, using it to frack another well, that's happening very significantly in the Marcellus Shale, probably more than in any other shale play in the country, driven not because of water scarcity. Pennsylvania has more river and stream miles than any state aside from Alaska. Okay, there's lots of water in Pennsylvania. The problem is that there's a severe constraint on the places that you can send this wastewater to be disposed of in an economically cost-effective manner. Okay, so as a result of that wastewater treatment constraint, most flowback from Marcellus wells is now recycled. We're up to, I think, about 80%, at least that's an estimate from the literature. But when you think about the sort of scale of the increase that we're expecting, again, going from 5,000 wells in 2011 to 60,000 wells in 2030, you do have to worry about, right, even if we're recycling 80%, right, if you increase the scale by that much, you're still really posing a challenge to sort of regional capacity for waste treatment. And in addition, as you think about the recycling problem, right, what I'm doing if I'm an operator, I'm taking that flow back, I'm going to go frack another well, but once most of the wells are in production, right, I sort of have no place to take that produced water, which is going to be generated over the life of the well, right, not just in those first few days, and the produced water comes out at a much slower rate, but it's much higher in concentration for the types of contaminants that we're looking at here. So the chloride, for example, would be expected to be much higher, as would entrained radionuclides and other things that have kind of come up in the Marcellus. Okay, so in the long run, right, you have fewer places to just put that waste, right? You sort of need a place to put it. Okay, so another thing that, right, if somebody's going to present results from a study, you always want to know, well, how does that match up against what others are finding? And in a series of studies that have come out, one of them just before ours, so Brian Lutz and his colleagues, he's now a faculty member at Kent State. He was a postdoc at Duke at the time that he did this work. But this was published in a journal called Water Resources Research, which is a really great journal. And he just sort of tries to quantify, right, what's the big difference in sort of wastewater capacity that is represented by, or necessary wastewater treatment capacity represented by the shale gas development in the Marcellus. And he's able to demonstrate that the total wastewater generated between 2004 and 2011 in the region had increased by about 570%, right, just causally attributed to shale gas wells, which is a big increase. Okay. There's some really interesting work happening by Jean Van Briesen and some of her colleagues looking at what the impact of partially treated waste disposal in Pennsylvania rivers and streams is on the probability that drinking water treatment plants downstream will violate standards under the Safe Drinking Water Act related to the types of contaminants that are in the raw water that they're drawing in. And that's very interesting work, and again, sort of consistent in many ways with what we're finding. Okay, they do find these links, and what they're concerned about in their case is bromide, which is also dissolved solid. Okay, so we didn't look at bromide, but again, one could do that on the large scale there as well. And then there's a really nice study that just very recently came out in Environmental Science and Technology, where, again, another postdoctoral researcher at Duke has gone and sampled both the sort of effluent coming out of the pipe for some of the industrial waste treatment facilities that are in our data set as well as stream sediments downstream of those plants, and showing, again, not surprisingly, right, that when you sort of test that partially treated waste that's high in chloride, high in bromide, and then, as I mentioned, most of these are conventional pollution problems, but that doesn't exclude, right, the idea that there could be some more unconventional problems, and I think highlighted by their study, one of them is that radionuclides made from the waste related to shale gas development in the Marcellus may be accumulating in stream sediments downstream of these waste treatment facilities. So that's of potential concern as well. And then in terms of the stormwater issues, I think that's really received a lot less attention. So we don't, to my knowledge, there's no other study showing the kind of impact that we demonstrate. And that could be a really important and interesting issue as the scale of development increases dramatically in that part of the country. Okay, so if I was going to sum up, I'd say, shale gas development can negatively impact water quality in local rivers and streams. That's what we show in the work that we've done. But I want you to sort of think about things like, right, partially treated waste coming out of permitted waste treatment facilities into rivers and streams. This is a picture of the outfall at Pennsylvania Brine, the Josephine plant, which is one of the industrial treatment facilities that is in our data, one of the red triangles on our map. Or, right, the sort of aerial, this is an aerial photo taken by Nature Conservancy of Development in Pennsylvania. Again, you can see, right, there's one well pad down there in the corner. There's another one off in the distance in that sort of northeastern corner. The sort of clearing of land for pipelines, right? Those are the kinds of pictures that you should probably have in your mind, more so maybe than something having to do with hydraulic fracturing itself, right? I mean, you take pictures of the process, it looks heavily industrial, it is heavily industrial, it looks potentially heavily polluting, right? The question is, where's the evidence, right, for the idea that it is in fact heavily polluting, at least in the case of surface water. Okay, so we're mounting evidence for the partially treated waste problem, but no evidence as yet of systematic spills from wells, even though it would be eminently feasible, right, given the technologies that are in play. So what are some policy implications of this? I'm a policy person, so I always have to end with that. The first is that when people, so I was asked this summer to write a paper for a National Research Council committee that was thinking about regulation and governance, okay, of unconventional oil and gas. And sometimes your first instinct is to say, okay, what new regulations do we need, right? Is there some new regulatory framework because of this new sort of technology framework and this new extraction framework that we're experiencing? And my sense there is that, if I talk about these kind of conventional pollution problems, I mean, gas wells themselves aren't permitted facilities under the Clean Water Act, but the wastewater treatment facilities, those red triangles, those are. Okay, so there are sort of monitoring and enforcement of those facilities. There are agencies that worry very much about what's coming out of those pipes and do regular measurement and reporting. So my sense is that if that's one of our biggest concerns, that the sort of issue of partially treated waste can be addressed in the existing regulatory regime. But it's also true that sufficiently dealing with that volume of new waste could increase disposal costs, or certainly will increase disposal costs for operators. So that's important, for thinking about how that affects the pace of development and prices and so on. Then if you're worried about sort of on-site pollution prevention practices, okay, if I'm worried about the probability of accidental releases, or even just that erosion and sedimentation problem that I talked about earlier, then there sort of is an existing framework that governs that as well. It's the liability framework. Okay, and that may or may not be sufficient, Given the empirical evidence thus far, maybe you could say, well, maybe the incentive, provided by the possibility of being legally liable for damages, if I have an accidental release, has been sufficient. You can't really conclude yes or no on that from what we've shown. But I do think that opens sort of very interesting questions about what else you might do. Okay, so firms, for example, are required in many states to post bonds, when they engage in the construction of an oil and gas well, or they have minimum insurance requirements. In Pennsylvania and in most other states, those requirements are really small. Okay, so I think in Pennsylvania you have an option of something like $5,000 for a well or $25,000 statewide. Okay, that might not have those numbers exactly right, but it's small numbers, relative. So if I have to post a $5,000 bond, but there's very significant damages that flow from my activities at that well, $5,000 is not going to cover it. Okay, so one thing that one could think about would be to look and see whether these sort of variation in bonding and insurance requirements out there have had any impact. And then you could think about whether those need to be changed to provide an additional incentive for sort of careful behavior. And then finally, that runoff issue, that one seemed to me sort of even more eminently solvable in some senses than the wastewater treatment problem. Only because, what we have is an existing loophole in federal regulations. It sort of says construction sites, that are less than 5 acres have to install this stuff. But if you're a construction site for oil and gas, then you don't. Okay, and there's sort of not really any rhyme or reason from an economic perspective about why you would make that exception. So one could try and estimate what would be the cost of including oil and gas construction sites within that framework under the Clean Water Act, and can we quantify what the benefits would be, and try and think about whether we would make that change. Okay, I have plenty of other stuff. If people want to talk about the actual regression results or anything like that, I've got them, so feel free to ask away. Okay, so the first hand, yes.
You'll probably be delighted. I was hoping to see the regression results,
Oh,
specifically relating around the question of
I am delighted.
how you weighted the different treatment plants, whether you
Yeah.
had the data on the number of deliveries per year, things like that, and then also the
Great
geographic
question.
component.
Okay, so with the wells, as I said, the sort of red X's are coming in on a continuous basis. I mean, sort of look one day and there's a well there, and then the next week there might be two, So that change is happening very fast. The waste shipments are changing more slowly, or I should say the reporting of the waste shipments is changing much more slowly. So what we have between 2000, well, the first waste shipment we actually see in 2004. So between 2004 and 2009, we see the waste shipments data only every year. And then between 2009 and 2011, so for those last 4 periods, we see every 6 months, so twice a year they begin reporting. And so there, that variation over time isn't going to be that sort of continuous variation. It's just we only see, these sort of very kind of discrete chunks. And so what we do is, so this is the basic regression equation. So this is for chloride, but basically the same idea for TSS. So I'm going to regress the chloride concentration that I observe at monitor I on day T. So I'm just going to, every time somebody pulls, or not a person, but every time the monitor pulls a sample and we have results for it, we're going to count that as an individual observation. Okay. And then I'm going to say, okay, I'm going to try and first control for all the stuff I think might be happening, right, in that monitor's watershed, by first regressing it on the average concentration at that monitor for all days between 2004 and 2000 and 2011. Okay, so just what are average chloride concentrations there at that spot? What are the average concentrations in that monitor's watershed, right, in that calendar month? Okay, so if it was January through December, right, we'd expect that the chloride concentrations to vary with road salt applications and other things, right, and we want to allow those trends to differ across watersheds. And then we're going to say, what about if there was something special going on in that month? Okay, so I'm going to say, what was the average concentration, right, across all Pennsylvania monitors in that particular month? Okay, so comprehensive set of controls. And then how much did it rain on the day the monitor drew the sample in plus the 3 days prior? Okay, because that's going to dilute chloride. And then the things that I'm interested in are these wells variables, that's the W, and the treatment plant variables, that's the T. And what we do is we take, for the wells, we do several different things. Okay, first we do basically kind of an upstream density. I wish there was a whiteboard here too. But what you want to think about is each well, right, is in a watershed, and upstream in the watershed, right, each monitor is in a watershed. Upstream in the watershed, there's some number of wells, anywhere from 0 to very many. Okay, and so what we're going to do is we're going to count the number of wells that were in the watershed upstream of that well on the day the monitor sample was drawn. And then we're going to divide it by the upstream area of the watershed. So it's like the spatial density of wells that were upstream of that monitor on the day the sample was pulled. Okay, and again, that could vary week to week, right, as more and more wells are drilled. Okay, so that's what the main wells variable is, and the same for the waste treatment. So I'm going to take the number of facilities that were accepting shale gas waste on the day that the monitor sample was, or in the period that the monitor sample was drawn, divided by the upstream area. So sort of density of shale gas waste treating facilities. And then we do several other things as well, okay? So in the wells case, I told a story where I said if the effect from wells is like chloride downstream, I'd kind of expect it to be from moving all these fluids around from place to place on the well site, right? And so we say, well, if I don't see any impact of the wells, which I don't, right, you can sort of see that gas wells upstream variable, the second row, is not statistically significant in any of the specifications. What if I just look in that window, right, of time where the fracturing and completion is taking place, when I really think those fluids are going to be moving around in large quantities? And there we don't have completion dates for most of the wells in the data set. So we take, for the ones that we do have, which is about 1,800 out of the 5,000, we take the average number of days between the spud date, the day that the drill bit hit the ground, and the completion date. And then that was about 80 days. So we say, well, let's look just at that window, right, the sort of density of wells upstream that are just in that window where they might be being fracked and completed. Okay, that's what that third row is. And again, there we don't see a significant impact. And if we go out between 90 and 180 days, we also don't see a significant impact. So we sort of looked at various ways. We also, in the waste treatment specifications, we also looked at the quantity treated, because the DEP tracks that. But those, in our view, as we explained carefully in the paper, are much less reliable than the sort of location of the treatment. So we're a little bit careful about interpreting anything there. Okay, and then this is breaking out by the facilities that were accepting waste and those that were accepting waste and targeted by the regulatory change. And this is where that effect that I mentioned sort of at the end there was coming out. Yeah, these are the regression, the parameter estimates, the coefficient estimates, and these are the standard errors in parentheses. That's right. They are large, but again, so we think about the way that the variable is specified there, right, is that divided by square kilometers in the watershed, right, so you have to make that conversion, which is why, right, when we actually go to interpret these, what it turns out that a 1 standard deviation increase in the number of facilities upstream accepting waste causes a 10 to 11% increase in downstream chloride concentrations. Okay, so I mean it looks big, right? Because the background chloride concentrations in Pennsylvania over the whole time period for all the monitors is about 20 milligrams per liter, right? So that's that 2,000 such and such looks huge, right? But when you sort of adjust for the fact that it's divided by the upstream area, the impact is not as big as that sounds. Yes.
Hi, I have a two-part question. The first part would have to do with, you mentioned the number you had in the first slide or two, the number of diesel trucks that need to, so I would think that would be a pollution analysis that needs to be followed through, because if you're filling these trucks with water, they're going to be extremely heavy and they're going to be burning a lot of diesel, which is particulate, and that's a carcinogen.
Yep.
And also in these remote areas where you have small roads, you're damaging the roads.
Yeah.
And those are more costs to the municipalities and so on.
Yep.
And the second part would have to do with the life of these wells. And if they're relatively short and you're talking about going into the future with tens of thousands of more, I think you're looking at a pretty big impact on, when they're clear cutting for pipelines and things like that.
Yeah.
That it's really going to start looking like a patchwork over the whole state.
That's
and
right. Yeah.
That's pretty scary.
Yeah, you're naming a lot of really important, other environmental impacts. And I will say some of them, so the habitat fragmentation, the issue of, this footprint, basically the sort of clearing of all this land, that came up in our expert survey as one of those 12. So that was clearly an important impact. The local air pollutant impacts from trucks and so on didn't pop out as being one of the sort of high priority risks, which was interesting to us because as economists, those local air pollution impacts tend to be the big sort of dollar impacts when we think about monetizing that stuff. And what I will say is that I don't know of some, I'm sure there are people working on the local air pollution impacts per se. At RFF, there's actually some analysis of the second piece of the transportation aspect that you just mentioned, which is the road use, where there's a study, actually Lucia, one of my co-authors here, and Alan, another co-author, I have a study on impacts on accidents. Okay, so on serious accidents, minor accidents, and so on. And not surprisingly, with all of these sort of this extra heavy truck traffic on the road, you see a very big spike in accidents involving trucks that happens contemporaneous with development and contemporaneous with the sort of number of wells in a particular area. So that's a really interesting. These are all super interesting and important questions. And what the economists would like to do is sort of add up all these externalities, try and understand on balance, are we all better off, despite them? How might we regulate them? In truth, it's hard to count all of these things. And even if one does, it's hard to think about what's the kind of right regulatory mechanism. In many cases, again, even the local air pollution problem, that's a conventional pollution problem. It's regulated, And if there are places that start to violate, the national ambient air quality standards for things like particulates, And we've seen that already in parts of the West for ozone, where there's a lot of shale gas development, Hopefully that framework will be sufficient to address those problems. It's a great question. Yep.
Thank you again. Excellent. A couple questions. Does that 2005 Federal Act, it may exempt, was it the Clean Water Act, but does it preclude the states from enacting their own requirements?
No, it doesn't. And in fact, as I said, in Pennsylvania, so the way it works is, so the National Energy Policy Act, it was just the Clean Water Act has stormwater control requirements for construction sites, but oil and gas construction sites are exempted as of 2005. But it doesn't exempt states from having more stringent regulations. And Pennsylvania does have these sort of permitting requirements. They, people come out, they inspect, but it's much less clear. What specific things does one have? But on the flip side of that, I think major operators, they come in, they're going to drill a well here, they're going to drill a well there. They're going to engage in basically the same practices, from place to place. It doesn't behoove them necessarily to weaken their stormwater control, investments because this state has a somewhat less stringent rules. So we see a lot of that stuff being installed in Pennsylvania, despite the fact that given the size of the sites, they wouldn't necessarily have to do that even under the state law.
And it also does not in any way exempt them from liability?
No,
okay.
No.
And then what about wellbore integrity? Sort of along the same lines of more traditional things that aren't new technology. Fracking has been around since the 40s at least.
Right.
And having wellbore integrity to not contaminate groundwater is not a new concept.
Yeah.
Well before this shale gas revolution. Are you working on anything with that as far as the different formations that may have more susceptibility because of the depth that isn't quite like what we have in Texas up in Marcellus, and then any extra requirements to try to ensure that there are good actions as far as wellbore integrity in cement jobs?
Yeah, that's a great question. So, I have a colleague, Nathan Richardson, who's a lawyer, and he's done this really interesting study on how various shale gas regulations vary from state to state. And as you can imagine, the sort of well integrity regulations are one of the things that just varies a ton in terms of everything from setback requirements to casing and cementing requirements. And it's hard to explain, right, what the source of that variation is. Is it the geology? Is it something else? It's sort of hard to know. So there is a lot of variation in how states are dealing with that. But again, that's something that I would sort of say is a little bit like the stormwater question in the sense that the major operators would tend to have a sort of modus operandi, right, that they're going to apply across a lot of places, and it's going to sort of meet some pretty stringent requirements, even if the state that they're operating in doesn't necessarily, share those requirements with other states. In Pennsylvania, this has been the sort of question of well integrity and groundwater contamination has been examined already pretty intensively in an academic sense. I guess I should say intensively. I mean, there are a handful of papers, but relative to other potential environmental impacts where there's sort of no evidence at all, either way, I think it's pretty well studied. But there's a lot more sort of ongoing work. Some of the most important groundwater studies that I can tell you about, so there's the sort of theoretical question of whether you could even in the Marcellus Shale have migration, of fluids from the formation itself upward into overlying groundwater aquifers, which are really, really far above. And there's debate about that. So there's a paper in the journal Groundwater that says, yes, in fact, it's possible, and indeed, we probably will see it, and then a kind of comment and reply that kind of goes back and forth in that journal about that. And then there's also some empirical studies that are just looking at, okay, let's kind of go out there, let's get some data on groundwater quality and proximity to shale gas wells and see if we can find some causal links there. And the first paper there was just a couple of years ago where the researchers, and these are again researchers at Duke, where most of the groundwater work that's been published so far in the Marcellus has happened. And they show sort of these very reasonably convincing graphs, right, as close as you could get to kind of a causal feel without directly demonstrating causality. They show, as you get closer and closer to shale gas wells, you see higher and higher levels of methane in groundwater wells overlying the formation, right? So, but there are a lot of questions as to whether that's causal or not. They also look at the Fayetteville Shale, and they don't find evidence of methane contamination or brine contamination in the Fayetteville Shale in Arkansas. So they draw the conclusion that clearly this is going to vary from place to place. But the sort of the well casing and cementing and potential impacts on groundwater are certainly of great concern, and there's a lot of research ongoing in that. We don't currently, the team that I've been working with doesn't have any research on that question right now. Yes. In the front, yeah. Sorry, and then over in the Longhorn T-shirt.
Thanks, great presentation. My question is, so what kind of impact of those shale gas does this wastewater treatment have on those wastewater treatment facilities?
That's a great question. So part of the debate, the question is what kind of impact does the treating the shale gas waste have on the treatment facilities themselves? And the reason that's a great question is that some of those regulatory changes that I mentioned that happened in 2010, 2011 in Pennsylvania were targeted at exactly that question. And the idea there, right, is that if it's a municipal sewage treatment plant, and through 2011 there were still municipal sewage treatment plants that were on that list of the red triangles, the accepting facilities. And there, right, they're going to use some primary treatment techniques that involve bacteria. And if you send a bunch of salty water through those facilities, you're going to kill off, right, the bacteria that would be, right, doing a lot of that treatment. So there was a significant concern about that, and in part due to that, the POTWs, the municipal sewage treatment plants, are no longer allowed to, well, basically no longer allowed to accept waste from shale gas wells for that reason. I think an interesting question would be, well, in that time, right, that they were accepting waste, was there some compromising of the treatment capacity, right, the capacity to remove other contaminants? And, to my knowledge, nobody's done that work, but I think it's a really important question.
Also, in your regression results, you showed the non-accepting treatment effect. Those are still positive.
Yeah.
Not significant. Have you tested the difference between these two?
I'm glad that you asked that. So there's two things that I would say. Okay, so this is asking the question about, well, I said, most of the statistically significant impact that we measure from waste treatment seems to come from those facilities that were targeted by the regulatory changes, right? The ones that either can't accept waste any longer or have been, restricted in their capacity to accept waste. So, on the one hand, you say, well, that's problem solved, right? But what you're looking at, right, and you're right to look at that is, well, this is still a big coefficient. In fact, the coefficient, estimate is bigger in magnitude than this one. And in addition, remember that those number of red triangles was pretty small. So between 2004 and 2011, there are only about 50 facilities, I'm going to say 52, that are accepting waste at some point. And so then you split those into two groups, right, and you start to get really small numbers. And so our ability to really, right, estimate this with a small standard error is going to shrink. So all I can say, right, is that this is sort of a good sign in some sense, right, but we'd sort of feel better if this looked more like a 0 than it does. I mean, it is a 0, right, statistically, but it'd sort of be nice to know, right, that is just going to go away. In fact, if I take all of the targeted facilities, the facilities targeted by regulators, out of the regression, and I run this again, I get a statistically significant impact from these. So, right, this fact and that fact sort of caused me to say, I can't sort of say definitively, oh, okay, the regulations have solved the problem, right? What we sort of need is more time, more facilities, right, to do better with the statistics there. So that's a very good question. Yes, over here.
From what I could gather, like you're anticipating a 12 times the amount of wells increase in the Marcellus Shale. Do you have any forecasts as to how they will be drilled? I mean, do you anticipate they'll be occurring on the same well pads? Do you have any indication or?
Yeah, that's a great question. So it's relevant for two reasons. Okay, so the question is how many on the same pad. So, in Pennsylvania, the pads that I visited tend to have 6 wells, and they're very, very closely spaced. I mean, like 15 feet apart. Very close, right? 1, 2, 3, 4, 5, 6, and then each of those wells have, 6, in some cases, lateral wells underneath the ground, right? You're from a very small spot on the top of the earth, you're draining a very large portion of the formation under the earth. So in that sense, the footprint, right, relative to what we would have done to obtain conventional gas in the same quantity, right, out of that shaped formation, we're probably doing pretty well, right? So the sort of horizontal drilling itself is a significant advance in the ability to reduce the footprint of wells and well pads. But there's two things. So one thing would be, 60,000 wells, if you take that, say it's 6 on average per pad, then we're talking about 10,000 pads. Okay, so it's a sort of smaller than, right, 60,000 pads. But there are two things that we're looking at, right? There are two things that we find in the study. One is the impact from the flow of waste. And that, right, is going to happen from a well, right? There's not necessarily going to be less waste because I've got wells closely spaced on a pad, right? The more wells I have, the more waste I have. Okay, so that's not going to be solved by that problem. The total suspended solids problem, though, right, the sort of runoff problem, to the extent that we can minimize that footprint on the land, we're going to reduce that problem. So, right, the sort of more wells we can get onto a pad, to some extent, the fewer pipelines that we need or the fewer, right, branch pipelines that we need, sort of that has a cascading impact on the impacts on rivers and streams and other things, right? It's not just rivers and streams, but habitat fragmentation and other things as well. Yeah, that wouldn't surprise me. Oh, that's interesting. Yeah. I don't think in Pennsylvania that they've gotten to that kind of density, but again, things could have changed since 2011 for sure. But it is true that most of this, if you think about the big clusters of red X's, right, in the map, we're in north central Pennsylvania, so right at the New York border, which says something about the fact that New York has had a moratorium, right, that you can sort of see that, so right, that's the New York border. Okay, you can definitely see, right, that if there were hydraulic fracturing allowed or shale gas development allowed in New York State, we would see it in some of those lower tier counties. That's what's implied by that clustering at the border. And up there, a lot of that is state forest, and so it's pretty mountainous, and so it wouldn't surprise me, right, that sort of dealing with slope and stuff have been pretty challenging. Down here, right, there's the other sort of bigger cluster of wells. A lot of that is coming out of ag. There is some forest as well, but agricultural land is somewhat, I think, easier ex ante for the operators.
Yeah,